anyone wants more time? No objections. So, yes, as we've been mentioning before, in addition, one sort of salient feature of single-cell RNA-seq data is a sort of high number of dropouts. So we can try to sort of basically make this model more realistic by also adding, easily inflating the number of dropouts, so adding dropout noise. So to do that, we add an additional parameter to the command, where we basically introduce additional zeros in a way which is sort of proportional to the number of, or inversely proportional to the mean expression level. So, so this parameter will basically determine how many more zeros you get, or how often you'll have dropouts compared to having no extra dropouts. And so we have that aspect that we can use to sort of complicate the model even further, which of course will lead to making it more challenging to detect whatever the ground truth is, since we're effectively removing information. Another type of noise which has been reported is what's been labeled as dispersion noise. So where your distribution is typically over-dispersed compared to what you'd expect based on some sort of analytical model. So we can capture that quite easily in the Poisson-Beta distribution by introducing an additional variable, which we're calling S, which we use to multiply both the parameters alpha and beta are multiplied by the same value S. And what that will lead to, if you do some algebra, or you can see quite easily here, is that if you look at the mean of this distribution here, you see that if you multiply A and B by the same, all by the same value, then the mean remains constant. But whereas in contrast, the variance, you will see this if you multiply both A and B by S, it will increase. So basically, this is a way of either increasing or decreasing the variance while keeping the mean constant. So I've plotted this here. So here I'm basically only changing S, and I am plotting the variance and the mean in red and blue. And so what you can do is that you can basically explore what happens if you introduce both dispersion noise and dropout noise to this model, so you can see how the distribution changes and what happens in the presence of greater or lesser noise levels. So I'll give you a few minutes to explore that before we move on to the next section. Sorry.